Yeah, good afternoon. It's a real pleasure to be here, and it's my first visit to San Sebastian. And I was fortunate to enjoy, a wonderful workshop on long-range interactions in atoms and other systems for the last few days. But it's also a pleasure to now come here, and I've already learned a little bit about this special research institute in physics here in San Sebastian. So, yeah, I know that this is a general audience. It's not, you're not expert in ultra-cold atoms. So what I picked for my talk is spin physics, because I hope every physicist in some way or other relates to spin. And I want to raise some fundamental questions about spin physics, what happens when spins interact. But I also want to introduce you a little bit to the flavor of the experiments we can do with cold atoms. Cold atoms has really been an amazing field. Usually if a field is very active, you think after 5 or 10 years it's time to move on. But cold atoms has, in my life, I've stayed in cold atoms pretty much for 30 years right now, but I feel every few years I do something new. Because cold atoms is not so much a research field, it's a method to do very, very different aspects of quantum science. Whether it's, performing precision measurements, whether it's doing many-body physics, whether doing fundamental quantum science. So cold atoms is a system where you can implement a lot of good science. And this has really led to a continuous growth, and it's amazing that the field is just, it was already spectacular 30 years ago, and it's growing and growing because so many, especially young people, figure out what else they can do with cold atoms. Talking about young people, I was also young many years ago. And if I now talk about spin physics, this is the very first paper on my diploma thesis, on my undergraduate thesis in Munich, on spin relaxation in disordered materials. I went on into molecular spectroscopy and then to cold atoms. And I would say for 30 or 40 years, I didn't do any spin physics. But now, again, I'm doing spin relaxation. So it's sort of sometimes funny how, if you change fields, how eventually, you close circles. So I don't think I have to emphasize too much why spin physics is important. It is important for magnetism, of course, but also magnetic systems have been paradigms for quantum phase transitions. So if you learn about spin physics, you also pretty much learn everything you have to know about phase transitions. Spin physics is also very interesting for dynamics, for out-of-equilibrium dynamics. But also, there are many problems in physics and out of physics which can be mapped onto spin physics. Like a spin class is a formulation of the traveling salesman problem. So it's a small exaggeration, but I would say if you understand everything about spin physics, you probably understand everything in physics, because it's so interconnected. For most of the talk, I will be talking about this Hamiltonian. It's a super simple Hamiltonian, one of the simplest Hamiltonian you can write if you have many, many spins in a material. You only have next neighbor interaction, no long range, just each spin only interacts with the next neighbor. And the interaction is just given by, you can say, S1 dot S2, but there can be a difference, and this becomes important, between how SZ and SZ couple and how SX and SX couple. So in other words, when two spins couple, there can be a different strength, whether the spins are longitudinal along the quantization axis or whether they are transverse. But to a general audience, I would say it's amazing. There is one line, and it has so much and so rich physics in it, and many of the physics is even unexplored, because the equation is simple, but the solutions are very complex and interesting. So when I talk about spin physics, and I don't think I need a laser pointer, and here is the interaction between neighboring spins. A real stick, yeah. So I should explain to you what is the spin interaction we are studying. Because we have atoms in an optical lattice. I will tell you a little bit more later what this optical lattice is about. But the magnetic field of a single electron, we have atoms with unpaired electrons, so they have with a single electron. The magnetic field of a single electron is so weak that any magnetic fields, any magnetic interaction is almost completely negligible. So how do those atoms interact, and how, as I try to indicate here, if we have atoms in two different spin states, how can they form, for instance, antiferromagnetic order? The reason is they do it what is called super exchange. Super exchange is nothing else than second order tunneling, and I want to explain to you now how it comes about. So all you have to understand in order to understand super exchange, perturbation theory. So if you have a ground state and an excited state, and the two are coupled, you get an energy shift in the ground state by second order perturbation theory. And second order perturbation theory is, you have to remember that for the next 5 minutes, matrix element squared divided by energy defect. And now I want to apply it to atoms which are localized, and I can explain it to you for just two atoms localized in a double well potential, and then exactly the same physics will apply to many, many atoms in a lattice. And so what I'm explaining here will be also important for magnetic materials. So if you have two atoms, the ground state for my perturbation theory is one atom on each side. Because when two atoms are in the same site, they generally repel each other, and there is a repulsive energy called U. So therefore, in my perturbation theory, I have two states. This is the ground state, this is the excited state. The difference in energy is U, and there is possibility of tunneling T, and therefore, the energy shift due to second order tunneling in second order perturbation theory is T square over U. So the T square over U is really something which penetrates all spin physics which we are doing in those systems with atoms in optical lattices. T square over U. This is the spin-spin interaction. And it is not an interaction of spins, it's an interaction because atoms can tunnel. But now you would say, but that's not spin physics, that's just a correction. So wait a moment. So if I have identical atoms, so this is for two different atoms, and if one is spin up and spin down, they are different, they are distinguishable. But if you have two identical atoms, there is a bosonic enhancement in tunneling, because in matrix elements for bosons, you have the square root n plus 1, and n is the number of bosons in the final state. So if you tunnel and you have now two bosons, the matrix element is not is multiplied by square root 2. So therefore, for the bosons, the energy shift has now doubled. It is 2t square over u. So therefore, when you if you had a system of bosonic atoms in two different spin states, there is an extra negative energy, there is lower energy when a bosonic atom has an identical atom in the same spin state as its neighbor. So this is now not in terms of, so this is, so the result of it is that we have here a spin-dependent interaction, and you understand now why bosons in generally want to be ferromagnetic. They want to be surrounded by atoms in the same spin state. Okay, let's play but now we can play games, because as I want to tell you later, we have control over the interaction of two atoms. And if two atoms are together, there could be actually a difference between the repulsion of two atoms in different spin states and in the same spin state. So if we have an extreme difference between U up and U up down, we can actually change the rules and we can make bosons to behave in an antiferromagnetic way. Okay, let's move on to fermions. If you have fermions in the identical spin state, you would say, okay, is it possible to tunnel? Well, the first answer is no, because with the Pauli exclusion principle, tunneling is forbidden. But well, in principle, you can go to an excited band, but I will use the single band approximation. So in the single band approximation, it's forbidden, but if you have an excited band, it is allowed. But then the energy defect is the band gap, which is huge, and therefore, indeed, the second order tunneling correction gives you close to zero. But if the two fermions are in opposite states, we have the distinguishable atom, we have minus t squared over u. And what we learn from that, when you compare the two, fermions want to have an opposite spin as neighbor. And therefore, they tend to be antiferromagnetic. So this is the kind of spin interaction which we find in cold atom system. And so people have formalized it many years ago. If they have bosons or fermions in two different spin states, I show one in red and one in blue. These are often pseudospins and hyperfine states, but it's two different spin states. And you write down the famous Bose-Hubbard or Fermi-Hubbard model. You have tunneling between neighboring sites, and then you have an on-site interaction. When two atoms are at the same site, there is an extra energy, an extra interaction energy U. So this is a fundamental Hamiltonian. But if you now mathematically transform it for small tunneling, you treat tunneling in second order perturbation theory, you can actually derive this generalized spin Hamiltonian. And I think I gave you a flavor why there is now spin-spin interactions which can be ferromagnetic or anti-ferromagnetic. And this is the Hamiltonian we have studied in the last few years. So to study spin Hamiltonian is important for physics, and people have worked on it in many different ways, in many different places for fermions and bosons. They've also used other systems like ions or Rydberg atoms to implement spin Hamiltonian. However, until recently, almost all studies were done for what is called an isotropic model. In other words, maybe let me just go back and remind you of that here in this Hamiltonian, the term which is SZ as Z and the term which is SS as X can have a different prefactor. If it is the same, it's an isotropic model. It would mean the interaction between two spins is the same. It doesn't depend, it only depends on the relative angle of the two spins, but it doesn't matter whether the spins are transverse or longitudinal. For many systems, there is a natural case that you have an isotropic interaction. But as I want to show you is, if you allow an anisotropic spin interaction, you actually can explore a whole different dimension. And I mean, that's something I learned. You sometimes think the simplest case is where you learn the physics and the rest is just details and complexity. But it turned out that the anisotropic spin interaction are fundamentally different from the isotropic case. So anyway, so that's my introduction to spin physics. Now, how do we do those experiments? Well, the cartoon of the experiment is we have ultra-cold atoms, typically at nanokelvin temperatures, and they are in a big vacuum chamber. And the vacuum chamber is important because that isolates the nanokelvin atoms from the room temperature environment in our lab. So I sometimes say an ultra-high vacuum chamber is the world's best thermos. These atoms are confined. If I simplify, I would say it's a box, it's a potential, but it's made out of electric or magnetic fields. And now we can do all sorts of experiments, and I will explain a little bit more to you, by just modifying the environment, modifying the spin states, modifying what's going on here with radio frequency, microwaves, with laser frequencies of different colors and all that. So that's the way how we talk to our atoms. We first prepare them, sometimes as a Bose-Einstein condensate, but then with laser beams, RF and microwave, we make them behave like, isolators, conductors, like, a magnet. We can create many different forms of matter by changing the rules of the game, by implementing Hamiltonian with the help of pretty much the whole electromagnetic spectrum. And sometimes I'm joking, I would say everything which atomic physicists have learned over 100 years, every way how to manipulate an atom, change the energy of an atom with external field, all that is now applied to make the game interesting for ultracold atoms, that they behave in a novel way and allow us to study new science. So in practice, this is how it looks in the lab. There is a vacuum chamber. The vacuum chamber is surrounded by lots and lots of optics that's needed to deliver all the laser beams. You see some very, very thick cables. They carry up to 500 amps to create strong magnetic field. That's another way to modify the properties of atoms. And the atoms are really sitting right here behind the viewport. So we do not need extra cryogenic shielding, because the atoms are transparent to the black body radiation. So if they are in ultra-high vacuum, they can be in full sight. They can just be sitting behind the window, because the thermal radiation, the black body radiation, they are transparent to it. This is very, very different from conventional cryogenic or low temperature physics research. And of course, we need lasers, and I sometimes love the view in the lab. This is an experiment where we use 3 different colors of visible light: yellow, red, and green. It's an amazing light show. In that experiment, I will not talk about it, but it's about sodium-lithium mixtures. Yellow is the color of sodium, red is the color of lithium, and green light is used for special purposes. Okay, I want to talk about atoms in a regular array in a lattice. So let me just explain, how can we create periodic potential? How do we now take a gas of atoms and line up the atoms in a periodic crystal? Well, our tool is light. And for instance, if we create a standing wave of light by retroreflecting a laser beam, we create a periodic modulation of the electric field. And just to say it simply, atoms are attracted by an electric field in the same way as ion powder is attracted by a magnetic field. So if you put very cold atoms into a standing wave of light, you get a periodic density modulation of the atoms. And if eventually you are in the limit that you have only single atoms, you really get single atoms lined up like the pearls on a necklace. So if you do it with 2-dimensional standing waves, they create a potential like an egg carton, or you can also do it in 3 dimensions. And that's sort of what we call an optical lattice. Okay, so I haven't told you how we cool the atoms. That's old history. We make atoms to nanokelvin temperature. We have them in a vacuum chamber. By multiple laser beams, we create a crystal out of those atoms. And now we want to do spin physics. And there is one ingredient which I have to show you, which is very important here. When 2 atoms sit together, are on one lattice side, they interact. And we have learned, and this is an important tool, to modify those interactions. And this is shown here. The normalized interaction is called scattering lengths. And when we simply vary an external magnetic field, you see we can do everything. We can switch off the interactions, we can make them repulsive, we can make them attractive, we can make them strong and weak. I don't want to say more about it, that the secret here is a resonance. When two atoms come together and there is a resonance, there is a bound state of zero energy, then the atoms stick together for a while, that's the resonance, and then they separate. Whereas if they're away from the resonance, they just do what you think is an ordinary collision, boom. And if they hang together, there is a much more intimate interaction, and this is causing all these effects we are using here. But the take-home message is, I mean, there's a lot of theory, lots of experiments behind it, but the take-home message is we have one knob, which is a magnetic field, an external magnetic field, and this can make the atoms weakly repulsive, strongly repulsive, attractive. That's the way how we control it. Okay, and so this is how we change the interactions, but I want to talk about spin Hamiltonian and said, what is really important is the spin anisotropy, whether longitudinal spins or transverse spins have the same spin-spin interaction, or if they differ, and that's called anisotropy. And the anisotropy is a special combination of the interaction between up-down, down-down, up-up. It's this combination, and I've just taken this graph and compiled it here as an anisotropy. So by varying the magnetic field, we can vary the anisotropy from 1. This is the isotropic case which has been studied before. We can go from 0, we can go to large positive and negative values. So this is kind of the new element we've brought to the field, that we can now study with cold atoms simple spin physics, but in a situation where the spin-spin interaction are anisotropic. Okay, yeah, so how do we study spin physics? Often the simplest case is, because we have the tools ready to go for it, to look for spin dynamics, to create an out of equilibrium situation, and then look for a relaxation process, look how the system responds. Sure, we also want to study, and we do that as well, that we create a system and want to study, is it ferromagnetic, antiferromagnetic, we want to populate the ground state. But I can tell you sometimes to populate the ground state is a little bit harder because you may need very, very low temperatures to reach the ground state. But sometimes an easier way is, instead of creating the ground state, you just have a system, you shake it and you see how it reacts. And the reaction of the system tells you a lot about what are the interatomic forces and what are the characteristic frequencies and such. So coming back to atoms in an optical lattice, we can prepare such a system very easily. We just take very cold atoms, put them into those 6 intersecting laser beams, and this is how it looks like. And this is a low entropy state. And then we initiate some interesting spin physics by creating a pattern of spin up and spin down. This is out of equilibrium now, but then we can watch what happens. So let me explain it a little bit more. So how do we create such patterns? Well, what we actually do is we take the spins, we rotate them by 90 degrees, and then if there is a vertical magnetic field, spins precess. So they are just turning around. But if you have a magnetic field gradient, that spin turns a little bit faster than that spin, and a little bit faster than this one. So in other words, what we create is a spin spiral. So we create those spiral pattern of spins, and the spiral pattern is actually with 2 angles, a periodic modulation. So if we have a spiral pattern, we can have a spiral pattern the spiral can involve the longitudinal component, or be only a purely transverse pattern. But if we now project it onto one spin state, we see a stripe pattern. A spiral, if you project it, becomes a stripe pattern. And that's what we observe. So to summarize, we have an optical lattice, we wind up the spins, very simple, just with a magnetic field gradient. The spins do the rest for us. Then we have those spirals, and we can observe that we have a spiral by just projecting with a laser measurement. We do take absorption of phase contrast images. We just take an image and we see the stripe pattern. I should also say that we do one-dimensional physics. We have arranged our lattice potential in such a way that there is only dynamics along one dimension. In the other two dimensions, we freeze out all dynamics by making this optical lattice very deep. So in other words, this is what we have. We have a bunch of one-dimensional systems. It's a three-dimensional crystal, but all the dynamics is in one dimension, and we have a bunch of those one-dimensional chains, and we image them all together by looking at this stripe pattern. Feel free to ask questions. Okay, so the stripe pattern is the signature that we've created this modulation. But now what will happen is, because it's an out of equilibrium state, with time, the system goes back to a homogeneous situation. The pattern, which is a non-equilibrium state, will just decay. And this is how we have done a couple of years of studies of spin dynamics. We create a stripe pattern, and we just watch as it decays. So we have a stripe pattern first, and then we have just a homogeneous mixture of spin up and spin down, and there is no pattern. It sounds very simple, but you can now study how this stripe pattern evolves as a function of lattice states. You can study it for different wave vectors, for different pitch of the spiral. You can study it for different magnetic fields, which change the anisotropy of the Heisenberg model. And you can look for spirals which involve a longitudinal component or which only have transverse components. So there's an enormous richness to be explored. So this is a typical example. When we look at this contrast, how it decays, well, it decays with a characteristic time, but we have also seen that it's in some situation not just a decay, but it oscillates. So, well, if we now vary the winding pattern, the pitch of the spiral, here we go by a factor of 2.5. So one is sort of narrow, is tightly wound, and in the other case is more loosely wound. We have now different wavelengths, so we can look at the frequency of this oscillation versus wave vector, and this is how we determine a dispersion relation. I will show you a little bit more than, let me just show it here. So we determine a dispersion relation, and what we find is a linear dispersion relation. That's actually a super simple case, because what we have done here is we have studied the Heisenberg Hamiltonian where the anisotropy is zero. Zero anisotropy means there is no interaction between the spins when they are up, but there is interaction when the spins are in the transverse plane. And this Heisenberg model can be exactly mapped with a Jordan-Wigner transformation to non-interacting fermions. And so what we see here is nothing else than the dispersion relation for non-interacting fermions. And the slope here is nothing else than the Fermi velocity. Okay. Now I want to show you the crucial role of anisotropy. So from the data here to the data here, all we have done is change the magnetic field. But the magnetic field is affecting the interaction between the atoms and changes the spin Hamiltonian from zero anisotropy to being fully isotropic. I think there was a question.
Out of curiosity, what is the ratio between the length scale over which you can change the magnetic field, so the spiral, and the periodicity of the optical lattice?
The periodicity of the optical lattice is given by the wavelengths of light. So in our case, we use infrared light. The periodicity is 500 nanometer. and the lattice periodicity is called A. And what you see here is we've varied the spiral between 6 or 7 lattice constant to about 20 lattice constant. I will show you later experiments where we have even wound spirals which had only 1 or 2 lattice constants. So we went pretty much as tight in our winding as possible. The longest winding pattern is simply determined by the size of our sample. And our clouds in cold atom experiments are sort of typically 10 or 20 microns. So we have maybe the size of our cloud is 40 lattice sites. And this is pretty much the longest spiral we can wind, that we just have one winding in the whole sample. I just want to sort of that you can really see very different physics, well, I would say with the naked eye. Because if you look here, we have roughly doubled the pitch of the spiral, and it takes about twice as long for it to relax. Actually, if we rescale the time by the length of the spiral, all the curves overlap. So that shows that when we scale time and length in the same way, this means ballistic, constant velocity. If time and spatial dimension are proportional to each other, this is constant velocity, and that means the relaxation is ballistic. That's not too surprising, because for this delta equals 0 in isotropy, we map to non-interacting fermions, and non-interacting particles would just propagate ballistically. But now for the isotropy case, you see something very different. When we change the length of the winding by the same factor of 2 or 2.5, there is a much more dramatic change in the relaxation time. And actually, did I show it? And when we can now make all the curves coalesce, but now we have to change length and time quadratically. And if distance is, if distance is quadratic in time, if distance goes with the square root of time, or therefore time and distance are related quadratically, this is the physics of diffusion. So what we have seen here is that there is a transition that's described by an exponent. Ballistic means time and distance are linearly related. Exponent of 2 means they're quadratically related, and that's the law of diffusion. So we've seen that depending on the anisotropy of the spin-spin interaction, there is a dramatic change in the characteristic of relaxation, going from ballistic to diffusive regime, and there are even super and subdiffusive regimes. Some of that is really challenging for an explanation. So this is where many body theorists really have to do hardcore calculations in order to understand that behavior. So this is kind of a frontier where experiments can guide theorists and theories can guide experiments, and that's how we make progress. Okay, so this was a situation where we had longitudinal spin, and longitudinal spin is related to energy, because spin up and spin down differ in terms of energy, and longitudinal spin can only decay by transport because there's a continuity equation for it. However, transverse spin can just disappear by dephasing. You may remember there's a difference between T1 and T2 times in spin relaxation experiment. And now we are looking at transverse spin. So the simplest experiment is if we have just interactions of x and y. So this is again the delta equals 0 case. So this is an So in the xy plane, this is isotropic. And so I can ask you now the question, if spins interact in xy isotropically, then by symmetry, if you have a ferromagnetic state, a magnetization which points into x, it's conserved. You can also point it in y. It's degenerate, but a classical xy ferromagnet would have a stable magnetization anywhere in the xy plane, but not for a quantum magnet. When we created a pattern in our quantum magnet, it pretty much decayed in the fastest time possible. That's pretty much just 1 or 2 or 3 super exchange times. So the reason is that, well, welcome to quantum mechanics. That's the difference between a classical and a quantum ferromagnet. The quantum ferromagnet decays by quantum fluctuation, because for the quantum ferromagnet to point to the magnetization which points in one direction is not the ground state. The ground state is a superposition of the spin pointing in all directions. And this is what we see here. So as a rapid dephasing, but it is only due to quantum fluctuations. There is no classical force, there is no classical torque. It is really, you can say, the non-commutativity of spin operators, or therefore the quantum fluctuation, which cause such a decay. Let me kind of move on to the next topic in spin physics. And this also, the topic of this research came for me as a little bit surprise. You think if there is a simple solution of a simple Hamiltonian, that people have found that in the 30s and 40s and 50s. But what happens is, in just 2 years ago, there was a theoretical prediction that this simple Heisenberg Hamiltonian would have exact eigenstates, and those exact eigenstates are spin spirals. So there was a prediction called beta phantom states, that there are beta because you usually solve one-dimensional spin Hamiltonian with the famous beta ansatz, and phantom states because there are states which contribute to momentum but not to energy, and the people who found those states called them phantom states because they are somehow live the life of phantoms in Hilbert space. Yes, please.
You talk about ground state or?
No, I'm talking about an excited state. So if you have, so I'm talking about this Hamiltonian, Heisenberg Hamiltonian with Nex-Neber interaction, and people showed that there are highly excited states which have a simple pattern. They are spin spirals and they will not decay. So there was a prediction that for certain conditions, we could take the spin, wind it in a spiral, and it would not decay at all. Also, it is highly excited. So that was a surprising suggestion, but the mathematics is sound. So we said, okay, let's try to find those states. And now I want to tell you in the next 5 or 10 minutes how we were able to catch the beta phantom. First, it's a little bit surprising, but you know, when you do, I learned it myself just when I did the research, any form of spin spiral would be classically stable, because the torque, if you have only Nex-Neber interaction, and if you wind a spiral, it's the symmetry of the winding, that the torque on one spin by its next neighbors just cancels. So there is no classical torque. But what makes all those spin spirals decay are the quantum fluctuations. And now I want to just illustrate to you here in a little cartoon picture why there is the possibility of a beta phantom state, of a spiral pattern which does not decay. So the torques cancel, that's classical physics, but also the quantum fluctuations cancel. So let's assume we have the Hamiltonian with anisotropy delta equals 0. So the spin-spin interaction only involves XX and YY. So And I want to show you that this pattern, which I've shown here, which has, well, it has 1, 2, 3, 4, it has a winding pattern, you know, after 4, you go 90 degrees from side to side, and after 4 sides, you're back where you have started. And I want to now kind of just give you the nice intuitive argument why this is really stable. It is stable because quantum fluctuations cancel. So let's focus on this purple spin, and each purple spin is surrounded by a red and blue spin. So the red spin on the blue spin point up and down, but the quantum but this spin is up or down, so the quantum fluctuation is, of course, you know, in quantum mechanics, the spin is not pointing exactly up. It has a little bit fluctuations, but the quantum fluctuations of the red and blue spin, because the spin has a specific quantum number in Z, is only in xy. So the fluctuations are only in xy. So how does fluctuating magnetic fields in x and y affect the purple spin? Well, the purple spin is aligned in x. Sorry, why does the I explained it differently. I've chosen here the coordinate system that y is up, x is to the right, and z is pointing out. So I just misspoke. So the red and blue spin are oriented along y, and since it fluctuates, the fluctuating interactions are in x and z. But now you see, the purple spin points in x, and precession of a spin requires transverse field. So an x field does nothing to an x spin. But what about the z fluctuations? Well, the z fluctuations do nothing because the anisotropic spin Hamiltonian has no SZ-SZ interaction. So therefore, everything cancels, and this spiral should be stable. And what people predicted is that this is for zero anisotropy, and I just showed you that if we go by 90 degrees, if we have a pitch of 4 lattices, this spiral pattern is stable. And the prediction was by the scope in Wuppertal that for any anisotropy delta, there is a special spiral which is stable. And what I just illustrated for you was the case when delta equals 0, then this, the wavelength of the spiral was 4 lattices. Anyway, I found it remarkable, an exact solution of a simple Hamiltonian which was not known before. So now what we did is the following. We, with the help of Feshbach resonances and external magnetic fields, I said it before, we can really change the anisotropy. And then, I mean, we took a lot of data for every anisotropy. We looked at the decay rate of the spiral. And in all the cases, we found there is a minimum where the lifetime is longest. And this minimum, the wave vector, the spiral wave vector, we found the minimum, followed the predicted equations. So this was clear evidence for the beta phantom state. If you ask, but yeah, wait a moment, but your minimum is not infinite lifetime, well, that's real life. If something is predicted to have infinite lifetime and you try to realize it in the experiment, you always have a finite decay rate. But it's not just purely a technical decay rate. Those phantom states are only eigenstates if they fulfill a special boundary condition. So ideally, it should be a periodic boundary condition. But since we have a linear system, we are not fulfilling the boundary condition, and there is some decay of the spirals which comes from the ends from the non-fulfilled boundary condition. What we found theoretically, so this was a prediction in 1 dimension. What we found theoretically, that there are also spiral patterns, which I'm showing here, in 2 dimensions. So it is also possible to have a 2-dimensional spin Hamiltonian and create a spiral pattern which should be an exact eigenstate and absolute stable. You would say, hey, what's the big deal to go from one dimension to two dimension? I know many people, especially theorists in the field, for them it is a big deal because the one-dimensional Heisenberg model is integrable. It has many constants of motion, and therefore to have certain things which don't decay and show anomalous thermalization is sort of very natural. But the two-dimensional Heisenberg model is non-integrable, and therefore to have some things, to have patterns which are long-lived are quite special because they imply that you can create some initial non-equilibrium state which would not thermalize, and that's related to the phenomenon of quantum scars, that there are regions in Hilbert space which would show anomalous thermalization. We would like to do that experiment in two dimensions because we do feel the two-dimensional experiment is even more profound than the one-dimensional one. Any questions? Yes?
When you say stable, is some kind of precession down, or it's really all spins staying and not moving? What is stable?
Stable means that the pattern is stationary.
Relative or just no
Okay.
movement?
When it comes to spin physics, people always do, go to a rotating frame. So it is stable in a rotating frame. So in other words, when I said we have a spiral, the spiral is always rotating around its axis, but it's not unwinding. The spiral pattern is the same.
Yeah.
So in other words, to use the example, a spiral is, it's actually a helix, not a spiral. A helix is a screw, and the screw is stable, but the screw is rotating because we have precession, overall precession in a constant magnetic field.
That's all for spin 1/2.
The prediction was in spin 1/2, but when we wrote our paper with a theory collaborator who also generalized it to arbitrary spin. So actually, those patterns are really special. They were predicted, they were derived from the beta ansatz, but eventually we could actually find a proof which doesn't involve the beta ansatz. It's very easy to once you know the solution, it's the first time you derive a solution, it may be complicated, but once you know a solution, you can explain it in many ways. And those special spirals are exact eigenstates, not just of one-dimensional Hamiltonian, also of two-dimensional Hamiltonian, and there's a generalization, I think, to arbitrary spin.
And this is for finite systems, so it's if you go to the thermodynamic limits, or
it is okay. There are special boundary conditions, but the simplest boundary condition is periodic. So if you take a chain of 100 spins and make a ring out of it, you fulfill the boundary condition for those spirals.
And then you go to the limit, the circumference to infinity. It still stays.
You can make the circumference to infinity, and of course, once you go to infinity, you don't have to worry about boundary condition. But for finite system, this is exact eigenstates for a finite system when it fulfills the periodic boundary condition. Actually, we hope that in the future we may even create, spin chains which are ring-shaped, because it's a beautiful system to study some of this physics.
Wolfgang, can I ask you, does it matter how the edge, so how you finish the chain, how the chain?
No, that matters. That is what I meant by boundary condition. When we have an optical lattice with a chain, we usually have what's called an open boundary condition, because eventually we have spins, and then we have nothing. That's an open chain. Yeah. And this boundary condition is not compatible with the exact eigenstate.
Yeah, no, this I understand, but I mean how this minimum goes. If the chain finish with some spin state or some other spin state, does this make a difference on the minimum? On how?
I don't think this has been studied.
So the energy there?
I think, okay, the deep minimum or an infinite lifetime would only be obtained if we fulfill the phantom condition in the pitch and if we fulfill the boundary condition. But our understanding is by fulfilling the pitch condition, we have eliminated the bulk decay, and this is really important, and the boundary is now introducing some extra decay, which was fortunately not dominant. So I would not expect the minimum to shift. I would just think there is a minimum, and the better you fulfill the boundary condition or the longer your chains are, the deeper it is. Let me skip this part. So there are some beautiful pictures. Let me finally, as sort of another indication what is possible in the field and how maybe we can still, with simple ideas, create new systems. Let me now change gears and talk about another kind of atom. It's the story of dysprosium atoms. And we also want to study spin physics in dysprosium atoms. But in this case, maybe I should. Maybe I should show this slide first. There is growing activities in our field, not using the standard atoms which have been workhorses for the field, sodium, lithium, the alkalis are simple. You just heat up a little bit of metal and boom, you have an atomic beam. This has been the workhorse of the field. But now in cold atoms, we are actually going through the effort and using other elements. And we are using elements, if you'd asked me a few years ago, what is element, 66, I wouldn't have told you that it's dysprosium. I mean, it's sort of lanthanides, it's deep down in the periodic table. And a lot of this work has actually also been pioneered by the organizer of the workshop, Francesca Ferlano in Innsbruck. She has started to work with erbium and also with dysprosium atoms. And the reason why erbium and dysprosium is, these are the most magnetic elements in the periodic table. Dysprosium has 10 Bohr magneton. It has a magnetic moment of 10 unpaired spins. And this is the highest magnetic moment you can get in the whole periodic table. So the reason why it is so magnetic is it has open F shells. And so it has 4 unpaired electrons. That's a lot. So 4 unpaired electrons is already giving you 4 Bohr magneton. But then because it's an F shell, there are orbital angular momentum numbers of 3 and 2 and 1. So if you add it up, you get 3 and 2 and 1 from orbital angular momentum, and then your 4 unpaired electron, it adds up to 10 Bohr magneton. It's really wild. And it's actually a nice teaching experience. I've taught atomic physics for many, many years. And now I've started to also teach dysprosium, because you realize it is the perfect atom for which all the Hund's rules add up to the maximum angular momentum. For instance, if you have shells which are less than half filled, I don't know if you know that, you have spin orbital angular momentum, and you have spin angular momentum, and you have orbital angular momentum. But Hund's rule tells us that the total spin and the total orbital angular momentum are antiparallel. But the rule changes when you have more than half filling, and this is what dysprosium has. So in dysprosium, it has 4 units of angular momentum of spin and 6 angular momentums of orbital, and they just add up together. When I said angular momentum, I misspoke. I meant magnetic moment. There's a factor of 2, of course, between magnetic moment and spin for the electron spin. So anyway, it's a really wild atom, but it's nature's perfect creation to make atoms as magnetic as possible. And if you have 10 Bohr magneton and have 2 atoms, their magnetic interaction is 100 times stronger than for alkali atoms. And now we have an opportunity. We have an opportunity to do spin physics by the real interaction, by the magnetic interaction between spins. The magnetic field of those dysprosium and erbium atoms is strong enough that we can now look at spin dynamics, spin interactions, which do not come from what I explained you earlier, from the super exchange and tunneling and such. No, we can now, in the previous example, the atoms only interacted because they hopped over and hopped back. They really touched each other in a, well, people would say in a virtual way, but what we call virtual is really real. It's a real effect. So this is how spin-spin interaction came. But now we have a situation that we can completely physically separate two systems, and there is spin interaction because the magnetic field of those dysprosium atoms is strong enough. Well, we wish it would be much stronger. It's just sort of a challenge to make it strong enough. And therefore, it's now a challenge for experimentalists to pull all sort of tricks. And we just came up with a new trick where we can put atoms. Did I press the wrong button? Yeah. Where we can put atoms not a wavelength away from each other, but 50 nanometer. So we are now using what we call a super resolution method which allows us to control and position atoms on a scale much smaller than the wavelengths. And the reason is, if you go from 500 nanometer, a normal optical wavelengths, to 50 nanometer, magnetic interactions are dipole-dipole interaction, which scale as 1 over distance cube. We get a factor of 1,000 more. So we have now a situation where we can make the purely magnetic interactions between two spins super strong by having a factor of 100 using dysprosium and getting a factor of 1,000 by going close. So the question is, can you use optical? I mean, you're all familiar with super resolution microscopy. It got the Nobel Prize in chemistry. People are now taking, pictures of cells with an optical microscope where the resolution is just a few nanometer. Absolutely amazing. So it breaks the rules of standard microscopy, but it's super powerful. But the question we were now raising is, can we also sort of manipulate position atoms much smaller than the wavelengths? So I think I need 5 more minutes to finish that. So if we take a laser beam and focus it, and we can trap many or single atoms in a laser beam, the size of the laser beam, because it's focused by a lens, is larger than the optical wavelengths. But can we now bring two atoms closer than an optical wavelengths? Well, the answer is yes. If we have two different atoms and they only react to two different colors of light, we can use two different colors. The two laser beams completely overlap, but if the laser beam is powerful enough, it will just create a tight trapping potential, tight optical trap, and localize an atom to 10 nanometer. So if you have two different atoms and two different colors of light, you can position atoms relative to each other by just a few nanometer. But in quantum science, we want usually indistinguishable atoms. I mean, you can do chemistry with sodium and cesium, but if you want to do resonance spin exchange or something, you want identical atoms. And so what we realized is that the dysprosium atom has also the following special property. Because it has 8 units of angular momentum, it is in a high angular momentum ground state. It has 8 units of angular momentum in the ground state, and the moment you have super high angular momentum, atoms have the property that circularly polarized light, sigma plus light, only exerts a strong force on the spin up atoms with +8, and sigma minus light on the spin down atoms. So it's the same atom, it's just in a positive or negative M state. And with that trick now, we can position two atoms, two identical dysprosium atoms, arbitrarily close. But the price we have to pay is, well, the limitation we have is one atom is in spin up and one atom is in spin down. And this just shows you the Clebsch-Gordan coefficient, and the larger the spin is, the more extreme it becomes. So you see here in blue that for the -8 state, the ground state, has a normalized Clebsch-Gordan coefficient from 1, but for the other circular polarization, the matrix element is 12 times smaller, and the matrix element squared, this is what determines the force exerted by the laser beam, is 150 times weaker. It's pretty amazing. Before I came across, I didn't even know that it would exist, that you have sigma plus light, you have a super strong force on spin up. You rotate the spin down, the force goes down by a factor of 150, and it's almost completely negligible. So therefore, we can now talk to two different spin states almost individually by using two different circular polarizations. So what we did is we created two standing waves with two different circular polarization. That creates double layers. So let me illustrate it like that. So we have a blue standing wave of sigma plus, or sigma minus, and a red standing wave of sigma plus. And each of them is only trapping the +8s or the -8. And by controlling optically the phase of the standing wave, we can now move those two optical lattices relative to each other. But in the end, the physics we are doing is of the two layers which are close by. So in other words, we sometimes say an optical lattice creates a stack of pancakes of atoms. We are now creating double pancakes, a double layer system. When I will talk now mainly about one double layer system, but it gives us a better signal to noise ratio because we have many copies of it. So this is our proof of principle that it works. We are now, how do you determine what kind of layer you have created? Well, if I had a very narrow slit and it is so small that it's smaller than the wavelengths, I can measure it by taking another slit and moving the two in a controlled way across each other. And then for a little bit of time, you will see there is light coming through. And what I'm saying is you measure the autocorrelation function of the slit. And similarly here, we are scanning the layers across each other. When spin up and spin down atoms come together, they don't like each other, they do chemistry, they form molecules, so there is an extra loss feature. And we could show that this loss feature corresponded to a width which was below 20 nanometer, and we didn't see any technical broadening of it. So we think we have single nanometer control over those layers. And let me quickly finish by saying one of the first experiments that we have magnetic interaction between two separated layers was done in the following way. Let me just say, we could just shake one layer and heat it up, but there is a cold layer next to it. And then we saw that the colder layer was cooling down the hotter layer without physical contact, just by magnetic fluctuations of the dipoles. And so we saw that there was a thermalization rate far beyond where the layers overlapped, mediated by magnetic dipole fluctuations. And of course, the further we put the two layers apart, the weaker becomes the dipole force between them. So we think there is many new things we can do. We are now planning to bring magnetic atoms close to each other in very different geometries. Right now we are working on two single atoms, and we want to put them close and see how can two single atoms interact with each other magnetically. But we also want to do it with layers and chains and do many-body physics of interacting bilayers. Anyway, sorry I went a little bit over time. I want to give credit to my group and the funding agencies.
Thank you very much for this very educative talk. And there were already some questions, but I think we have time for a bit more. First, you, then
So this DECX in the two layer, but what's the structure of the layer? Like, is it twisted or it's straight? Or
The geometry is, it's a Gaussian laser beam retro-reflected, and that creates a one-dimensional standing wave. So therefore, in each of the standing waves, we have literally a pancake. It's sort of a pancake which has a finite size because of the finite size of the laser beam, but it is flat, and the thickness is about 15 to 20 nanometer. So we have sort of like my hand, a 20 nanometer thick layer of atoms. Because it's a standing wave, we have maybe 20, 30 copies of it. But now we have a second standing wave with the opposite spin, same geometry, and the relative separation between the two is adjustable at the 20, 30, 50, 100 nanometer scale.
is it possible to realize it in the tri-layering? Like what for the Y layer, it has already been realized. But if we have like 3 layers.
I had discussions at the workshop, and actually with the theorist, he got me and I got him interested in tri-layers. The problem is we play tricks with polarization, sigma plus and sigma minus. Unfortunately, there are only 2 polarizations of light, sigma plus or sigma minus. You have only 2 orthogonal polarization. But what we actually dreamt up, Francesca, is to take maybe dysprosium and erbium, or take 2 different dysprosium isotopes, because then you can create one layer in one color, the other layer is the second color, and then you have polarization. So if you have 2 different isotopes, so if you take erbium and dysprosium, you multiply things. So if you have 2 different isotopes and use sigma plus and sigma minus, we can do up to 4 layers, and each of the layers can be positioned with nanometer precision. But I think we have enough to do with 2 layers for now. But people were asking me if we can make two layers of fermions and put a bosonic layer in between, and the bosonic layer is causing, indirect pairing of the fermions in the upper and lower layer.
Nice.
Thank you very much for the talk. I have 2 questions. First one was more in terms of the experimental setup. So you mentioned the use of lasers. Has there been any case of studying this system with polarized neutron scattering? Because neutrons are very good at detecting the dynamics of stuff, but I have to imagine the experimental setup is very complicated.
The answer is no. We say we have 100,000 atoms or million atoms, but even a million atom is less than a femtogram. So for every chemist, for so many other techniques, it's nothing. So I think it would be very, very difficult to get a signal from neutron scattering, because the cross sections are so small. On the other hand, why should we do neutron scattering? People do neutron scattering to see magnetic structures, to probe sort of spin patterns in solids. We can do that using circularly polarized light. Because why do people do neutron scattering and not X-ray scattering? They often do neutron scattering because neutron scattering is spin sensitive. But if we use circularly polarized light, which couples different to spin up and spin down, we can get the full spin sensitivity out of light scattering.
It just depends on the cross section. With usually with X-rays, the mismatch of the cross section of the neutrons.
Yeah, but we don't use X-rays. We use the resonant light which is in full resonance with the atoms. And if you use light close to resonance, our cross section is lambda bar squared. It's an optical wavelength squared. So I'm just saying this is orders of magnitude more sensitive than any X-ray or neutron scattering method, but it does exactly the same.
I guess it's easier to generate the neutrons with more expensive also. Thank you very much for the answer. The other question I had was, you just talked about dispersion. This true dispersion has a very nice moment. What about chromium? Because I know chromium also can have way a bit smaller. Are there any experiments or
You talk about chromium,
holmium?
holmium or chromium?
No, holmium. H-O.
Holmium. Is a Max Huffman had an experiment as a less magnetic moment than dysprosium and erbium. It's like
I
4
forgot
mu
what the magnetic moment of, do you
B.
remember?
About 4 mu B, I guess.
It's how much?
4.
4 Bohr magneton. I mean,
Holmium.
there are other candidates. Chromium has 6, has also unpaired electron. And Francesca just reminds me, holmium has 4 Bohr
I think
magneton.
so. 4.
So 10 is really the maximum. You can't beat it.
So holmium plus. Plus. Maybe I'm thinking about chromium also. I'm not my out.
Mm.
I mean, I could prove to you if I play Hund's rule and put electrons into F shells, the maximum graduate student in the thesis was going through all the F shells, putting 1, 2, 3, 4, up to how many 14 electrons into the F shells, and he clearly showed that the absolute maximum magnetic moment is 10. So you would say, put in 7 electrons into F shells, and you have 7 unpaired electrons. Great. But since you, according to Hund's rule, fill up the -3, -2, +2, +3 with 1, you have only 7 unpaired electrons, but no orbital angular momentum. So you get stuck if you're at half filling, you get up to 7 Bohr magneton. Whereas if you play the game and you do not have half filling or full filling, you also get orbital angular momentum. So it's really this interplay of getting orbital and spin angular momentum, and nature has maximized it with dysprosium.
Yeah, because with holmium you wouldn't only have
My question, you used Heisenberg Hamiltonian, you talk about this, but you never mentioned magnons. So they never appear here as natural excitations, just spin waves, magnons as excitations in the Heisenberg model.
People in Munich have studied, single magnons and have studied double excitations and have looked at interactions between 2 magnons. I didn't mention it because we didn't study it. You can put it in this way. Magnons are sort of the basic elementary excitation, whereas the spiral is a huge excitation, kind of, you can probably write it in some magnon basis, but it would involve many magnons.
Exactly, maybe it's a lot of magnons.
Yeah.
It's the same field. So
This dispersion, it was for magnons, isn't it? When you map it,
the dispersion
Heisenberg,
relation.
this dispersion relation. This continuum.
To be right, yes, actually, this was a little. The linear dispersion relation would have been the dispersion relation of magnons, but it was almost surprising that we found it because the spiral is such a strong excitation that you would expect the weak excitation limit not to apply. And probably the fact that we found a slope which was not 1 times the Fermi velocity of the after mapping to fermions, it was 0.8 or 0.9. This probably means that we are a little bit out of the perturbative regime of magnons.
So I think we had a lot of questions. We should defer the further questions to the brief meeting after the talk in the kitchen. And let's thank Professor Ketterle again.